All right, so finishing the slides from Monday, the homework problems. Easiest way to do these problems is an equation solver, so you can type it in either way here, just using base SI units, where everything will be in joules per mole or joules per mole Kelvin is sort of shown here. The standard way everything is written on your sheet, though, of course, S is in joules per mole Kelvin, but G and H would be in kilojoules per mole. So the second form of the equation helps with that by basically converting everything to kilojoules per mole as our unit. Maybe that's potentially more convenient. So that's, yeah, S divided by 1,000 to go from joules to kilojoules per mole, and then R is also given here in kilojoules per mole Kelvin, which might be more convenient. If you type that equation in, let me fix, what do I have here? Okay, delete this extra 4, enter, and then go into my solver. So G is 0 is my equilibrium constant, delta RG is 0, H 61.4. I have a typo here. This G here is delta RG with no circle on it. This is delta G under any conditions, right? H is the delta RH naught, and similarly down here, right? S is delta RH, delta RS naught, but yeah, this G here is under any conditions because I'm adjusting for entropy. Due to configurational entropy as we change the pressures or concentrations. Then I can just plug in my H. Since I'm using that divided by 1,000 version, I'm just going to plug in H in kilojoules per mole, S in joules per mole. I'll do my 298. Remember, the way this works is that it's guessing the correct value here, so it might not give the correct answer here. When I originally typed this in here with Q equals to 1, it gives me an error and says there's no sign change. That's okay. I can go back in and fix that by just giving it a better guess. In this case, I know Q is going to be much less than 1, so maybe I'll guess, I don't know, if I guess 0, will that work? 0 probably isn't going to be good because it's in the logarithm, but what if I guess 0.00001? That's 10 to the minus 6. That could be a good guess. And now I can go in and do my, oops, I've got to go back to Q. So it's going to start from that guess and then eventually get to the correct value. This is 2.63 times 10 to the minus 6 is my room temperature value of Q, which is the partial pressure of mercury in bar. And again, what's so nice about this is now I can just go in. 40 Celsius is 3.15. For T, go back to Q, solve it again. At 40 Celsius, I get 8.61 times 10 to the minus 6 bar. So yeah, those are my two partial pressures at 25 and at 40 C. Again, very easy to quickly sort of solve for the unknown with this approach. It doesn't ask you in this case, right? But another thing you might want to know is what is the boiling point of mercury in the lab here? What if that heating mantle gets out of control and it goes to boiling? It turns out that atmospheric pressure today in the lab was 1.01388848, just getting the pressure off of sort of barometric pressure off of weather.com. So if that is the pressure in bars, my Q would be equal to that. If I clear Q and type that in, let me find that number, 1.0138. So that's the Q I want, right? So now I can type in Q and instead solve for at what temperature will Q be equal to 1.0138 if I do my normal assumptions where S and H are independent of temperature. Now I can go alpha, enter. And I can see 620 Kelvin is the boiling point that it's sort of chosen here. How close does that actually agree? Again, you can see that. In this case, 620 Kelvin is a lot different from the 300 Kelvin we are in the lab. So yeah, there's no real guarantee that this is going to be an incredibly close answer. Mercury's boiling point is 356.7, which is actually not in terrible agreement with 630 Kelvin. The guess we just made was 620 Kelvin. Really pretty good agreement, especially given how far we're trying to extrapolate H and S. We know the values at room temperature. 620 Kelvin, very, very different sort of temperature, but still pretty good agreement there. And so yeah, really almost all of the book problems you can do with what we've done so far, and most of the problems on the homework. Apply that normal equilibrium analysis, figure out, which is sort of the unknown you're solving for, maybe draw a G versus T graph, which thing is higher in enthalpy, which thing is higher in entropy. That one analysis that we've done really gets us quite a long way towards understanding all sorts of different chemical equilibria type phenomena, as well as, again, other problems on the homework. You do the Van 't Hoff plot, should be pretty familiar with what you've done previously. Make the correct plot, ln of k versus 1 over t. Use Linus and all of that, or regression tool pack to get all the parameters that you need, and go from there.